Okay, you have it back now. Okay, we can probably go ahead and get started.
Okay, yeah, thanks
Jay.
for having me. I'm really excited to present to all of you about Daft. So hi, my name is Jay. I'm a maintainer of the Daft open source project. And yeah, maybe just a little bit more about myself before we get started, and also just the rest of the team in Daft. So I'm working with Sammy. He's the CEO of our little startup called Eventual Computing. We have backgrounds in high performance computing and autonomous vehicles. And I've also worked in biotech and been dealing with these weird data types for a few years now. And Sammy's also been at a company called DeepScale, which sold to Tesla. And we met at Lyft Level 5, where we worked on autonomous cars together and worked on a lot of data involving LiDAR and images and radar type data. So really funky data types, and found ourselves just really needing a solution like Daft to work with these types of data at scale. And so maybe let's just move on to what is Daft really. So Daft is a distributed Python data frame, and it's a data frame. So if you've ever worked with a library such as Pandas or PySpark or the new Polars, if you've heard of that, a data frame really is just a table of data. And then all of these libraries that I've mentioned, these data frames have rows and they have columns. So it's two-dimensional. And every column has, column name and maybe a column type as well, such as a string, integer, and a float. And this makes it really easy to work with your data because then your data frames can do things such as filter rows, join two tables together, filter just for columns you want, or run computations on the columns. So Daft is distributed, meaning that it will work both on your local machine, on your laptop, where you have maybe 8 gigabytes of RAM and maybe 8 cores, but it will also work in a distributed context, in a distributed cluster. Let's say you have maybe 100 machines, thousands of cores, and terabytes of memory, and that's where it helps you scale up if you need to work on hundreds of thousands or millions of images, for example. Daft works really well on complex data. I'm going to go on to explain the term complex data in a little bit, but for now, you can think of complex data as data types such as images, video, audio, things that you don't really usually see fit into a table like a spreadsheet or in a CSV. And the reason why you may not have heard of Daft is because we only open sourced it about 3 months ago. So it's a fairly new project, but it's gaining quite a bit of traction, I would say. Yeah, we can maybe move on to an introduction of complex data. So what is complex data? And the question you may ask is, do I have complex data, right? Do I need something like Daft? So we see data as lying on some sort of spectrum between primitive and complex. Primitive data is data that we are, as programmers, fairly familiar with, right? So such things such as integers, like 42, or a string, such as the string foo. 3.14, which is a float, or true or false, which is Boolean. But then, oftentimes primitive data isn't as useful just by themselves. Many concepts require us to compose multiple primitive types together in meaningful ways for them to be useful. In programming, in object-oriented programming, we call these things objects. And here are some examples. For example, latitude, longitude as two floats composed together to represent a location on Earth as a coordinate, right, a geographical coordinate. And a person can be comprised of a name, which is a string, and an age, which is an integer, and the age has to be, above, it has to be more than 0, essentially. And so when we start bringing these primitive concepts together into these more complex types, they start having more schema, right? We can make more assumptions about our data. For example, age has to be more than 0, name cannot be empty, things like that. And then once we go to even more complex types, we can think about types such as images. How would we represent an image in memory? One implementation could look something like this, where we have a height, a width, and maybe a buffer of pixels, right? Maybe 1 million integers in this buffer. And this is complex because an image requires a lot more primitives to represent, and it also requires a lot more processing to be useful. One thing I find interesting, and that you may have heard, is a lot of people call images unstructured. But if you look at it, it actually has quite a lot of structure, right? It has a height, a width, there's a fixed number of pixel values. Oftentimes this fixed value, these pixels are organized as a grid with RGB, 3 channels. It has a lot of structure, but it's just a very complex data type, right? There's a lot more data in it, and it requires a lot more domain knowledge almost to interpret an image data type. So given these examples on the spectrum from primitive to complex data, let's try to observe some things about complex data, right? So first of all, complex data is composed of a lot more primitives. So an image, for example, has maybe 1 million pixels, and that's just way more data than something that's primitive, like a single integer. Complex data also tends to be very domain specific because they describe more domain specific specialized concepts. The example we gave before was the latitude and longitude, which isn't just a pair of numbers. They actually represent a location on Earth in a geographical coordinate. There's a meaningful relationship now between these two numbers that only makes sense within that context. We can then actually start to define domain-specific methods that may not make sense on any random tuple of pair of numbers, right? For example, we may want to convert a latitude-longitude to a zip code, and that only makes sense within this context. Lastly, complex data has structure, but it's often really hard to represent and requires these complicated ways of encoding. A video, for example, has these iframes, which are these almost anchor frames, and then diff frames in between, and that's how we encode videos. And so it often becomes really difficult to serialize and represent these data types in memory. And you have to have applications that understand how to read and write this type of data in order to work with it. And so here are some common solutions we have for working with data across from primitive to complex. On the primitive end of things, we have SQL. It's ubiquitous. Everyone kind of likes to use SQL. It represents your data as this table format, and it's a de facto solution for a lot of data querying. It's surprisingly good, actually, for some complex data types, such as lists and basic structures. And some dialects of SQL actually allow you to query, embedded JSONs, right, which you may think of as actually pretty complex data types because they have arbitrary nesting and list types within this JSON type. Some data engines give you the ability to define what's called a UDF, or user-defined function. This lets you encode domain-specific functionality into your application by writing your own functions. For example, you may want to write your own function in Scala or Python, and then have SQL run that function when you call it. So for example, Spark SQL and BigQuery and a lot of these other frameworks allow you to do these things in JavaScript or Scala. And then we encounter the tabular data frames. For example, Pandas. Pandas is a really popular Python data frame library, and I think it's actually one of the reasons why Python is as popular as it is, because Pandas is really accessible and helps you represent your data as a data frame in this tabular format. And so you can run very SQL-like operations on your data, but at the same time have the ability to pull your data out as Python, run some Python, and stick it back into Pandas. Another really popular and up-and-coming library is called Polars, which is, you can think of it as a faster pandas. And our Daft library takes a lot of inspiration from Polars as well. However, once you get to the really complex data types, such as images and videos and these like big tensors, oftentimes what we see is that most people end up building their own ecosystem of tooling and systems to process this type of data, right? You have libraries such as Pillow and NumPy to work with images. Maybe you have storage, different storage formats, and you have like a job queue, and you have compute provisioning to bring up the massive amounts of compute that you need to process this type of data. As you can see, the ecosystems of systems that you would use to work with primitive types in this like tabular SQL-like data structure is very different from the types of systems that we use to process complex data, because maybe we need GPUs or we need 1,000 machines, and the systems on the left just don't cut it. And that's why we built Daft. We wanted to kind of build this gap, and we believe that data kind of lies on the spectrum, and we should be able to handle everything from the primitive end all the way down to complex. And what Daft gives you is, first of all, it's a familiar data frame interface. So your data is always going to be rows and columns, and that makes it really easy for us to support all of the relational functionality that SQL provides, which is crucial, right, to working with primitive data, because you often have a lot of metadata. For example, when you're working with images, you have maybe this image was collected from a certain robot with a certain ID and a certain timestamp, and these are all fields that you want to be able to query and join and filter on. And so having this data frame interface lets us support all of the basic primitive types really easily. Second of all, Daft supports complex types by allowing columns to be of any Python object. So we have this really expressive typing system. We embrace the dynamism of Python's typing system. And so if your data can be represented as a Python object, then Daft can handle it. So you can have, PIL images. PIL is a common Python image processing library, or you can have NumPy arrays, and really any library that you work with can be used in Daft, and we can contain these objects within Daft column. Third of all, we have a really nice Python native UDF functionality. They look just like Python functions. And so this allows you, again, to encode these domain-specific implementations of functions that you might want to run on your data. For example, you may want to run a custom algorithm to process your images, or you might want to run a machine learning model on an image, right? And these are all functions that you can write and tell Daft to run on your columns. And last but not least, because as we mentioned, complex data is usually large and contains a lot more data in general because it contains a lot more primitives, you end up needing a lot more compute to process complex data. And so Daft is built for distributed computing over a large cluster of machines, and we use a framework called Ray to distribute our computation. And so if you have a Ray cluster, we can actually run Daft on that Ray cluster, and the code looks almost exactly the same as it would run on your local laptop. And so I'm actually going to show all of that that we've talked about. I'm going to show all of that to you through a little live demo. Hopefully this works. Live demos always have the habit of not working when I need them to most. But here in this demo, we're going to go through a simple example of using Daft to go through this data set that's called the open images data set. Let me zoom in to make sure that everybody can see. But so really, this tutorial is a very simple tutorial on how can we run algorithms on this data set and just sift out the most read, quote unquote, read images out of the data set. So first, I'm going to run Daft on my local laptop. So I'm going to specify this flag distributed equals false, which we're going to be using in this notebook to run some things conditionally, right? So with this flag, I am going to skip this cell, which is all the Daft configs you need to run in order to run Daft in a distributed fashion. We'll revisit this later. And now we're going to load some data into Daft, right? So to load data into Daft, all I have to do is tell Daft to load data from files. And here I'm giving it a file path, which is a folder in AWS S3 that I've populated with a bunch of JPEG images. And so by loading this data from Daft, from AWS S3 into Daft, we are running in a non-distributed way. And so we're going to hit this branch of code, which will limit our data frame to 100 rows. And so this data frame now is 100 rows. And if we try to display the data frame, you'll notice that it says, hey, there's no data to display. The data frame is not materialized yet. And this is because Daft is what we call lazy. So until you tell Daft to run, it's not going to. And it will just show you kind of the schema of the data frame as it currently stands. So as it currently stands, we have all these columns. There's a key column, there's a last modified column, there's a type column, and it's a size column. And I'm going to show you why this laziness is actually really useful for Daft, right? So to do that, let's actually filter this data frame and say, hey, we only want images where the size is in between 300,000 and 200,000 bytes, right? To do so, this is a syntax where you do data frame. I want the data frame where the column size is smaller than 300,000. So I'm going to run this. And then I'm going to run a second filter to say, hey, I just want the data frame where the column size is more than 200,000. So now, if you notice, these cells actually ran immediately. And that's because, again, Daft is lazy. So by running these two filter where operations, we don't actually run computation on the data. We enqueue it into a query plan, and we can see the query plan by hitting this explain method, and we'll see that actually we have these two filter operations. The first one filters for where the column is less than 300,000, and the second one filters for where the column size is more than 200,000. And then there are these limit operations, which limit our total number of rows to 100. And then there's some sort of a scan operation where it's reading these file paths from AWS S3. And you'll notice that actually, hey, this is quite inefficient if I run these two filter operations one after the other, right? You have to do two passes through the data set to run both filter operations. And so Daft does these optimizations at runtime where it optimizes this query plan. And all you have to do is tell it, hey, show me the optimized version of this query plan, right? And here we have now this filter, which is running both the size greater than 200,000 and the size less than 300,000 filter predicates, right? So at runtime, Daft will perform these query optimizations. In this case, what it did was it squashed the two filter operations into a single filter operation. But Daft also does a lot of really powerful query optimizations, such as column pruning. It will prune out columns that you don't use, or predicate push down. So it can actually push these filters down into the scan operation to make things faster when we're reading data from remote sources. So now that we have defined these filters, let's go ahead and call .collect, which will tell Daft, hey, I'm ready, run my data frame, show me some results. And this is the data that we are now pulling. You'll see that there are 10 rows that we're displaying here out of a total of 16. So after filtering our 100 rows, we now have 16 rows only. And all these sizes are between 200,000 and 300,000 as we requested. So we really only need one column, which is this name column. So I'm going to go ahead and prune this data frame down by calling .select. Just give me the name column, right? And I'll just show 5 rows. And this is kind of what our data set looks like right now, just this name column. Cool. So that's a bunch of pre-processing that we've done already. Now let's show you how to work with data that's more complex. So this name column right here, this is actually a URL, right? It's a string, but we interpret it as a URL, and that makes it a bit more domain specific and complex. And Daft provides a utility function over URLs. You can actually just call .url.download on the column, right? So in this case, what we do is we concatenate the string s3 : the prefix to the name column, and then we're calling URL download, and this pulls the data down as bytes and calls the new column names a new column image. And so now we materialize this new data frame, and it looks like, yep, now we just have this name column, and we have the bytes that we've downloaded from this URL as a new column, right? But we don't want bytes. We want images. That's what ultimately we want. And so we can define a simple function. This is what I was talking about earlier with user-defined functions. And so in order to do that, all we need to do is define a simple function that takes a bytes column and casts each byte into a pill image, which is a common image processing library. And we're also going to do a resize into 256 by 256 dimensions. And in order to run this function on our data frame, all we need to do is call the function like so on the column. And so this line is saying, run the bytes to pill function on the image column of my data frame and just override that image column with the results of this new column, which is going to be pill images. So let's go ahead and run this. And voila, now we have I think that was like 2 or 3 lines of code. We now have downloaded all the data from this URL as images and then casted them as pill images. And now let's go ahead and run a magical function that I've written here, which is this magic red detector function. The implementation isn't as important. Just know that this red detector function will be able to pinpoint all of the red pixels and kind of give us a mask over those red pixels, right? So running this function is as simple as calling .apply on the image column, and we apply this function on our image column. And this is what we get, this red mask, which is working pretty well. We see that this plane has these red stripes and it's getting picked up. We have these red chilies in this dish, and this red bag is really well activated. We see a lot of red in this red bag. So it's working pretty well. And now we just want to maybe do a sort to show us the top reddest images in this data set, right? And to do so, all we need to do is, first of all, let's sum up all of the white pixels in this mask by running this simple function. Again, we'll just apply it on the column. And then we are now going to sort on this new column, the number of pixels that are red, and sort it by descending. And now we collect it. And we see that, yeah, this bag is the reddest image in our data set. This is red painting, has a bit of an orange tint. And there's the plane, and then there are these images down here that have hardly any red in them. So this is all great. We're running now locally on our machine on just a limited number of rows. But let's say that now we are interested in running on our entire data set, right? We have a distributed cluster that we want to make use of, and we want to run it on our entire data set. So let's see what that looks like. I'm going to flip this flag to distributed equals true. And now we can run this cell, which shows you some of the setup that you need to run Daft on a ray cluster. So let's say you already have a ray cluster. I'm going to initialize a connection to the ray cluster, and I'll tell Daft, hey, I'm going to set the runner to this ray runner, which I have actually port forwarded locally into this remote ray cluster that I'm running. And so now that our distributed flag is true, we are going to hit this line of code where instead of 100 rows, we are now going to take a look at 10,000 rows in our data set. And we are going to repartition our data set as well into 64 partitions, which helps Daft run your computations in parallel across these partitions. And so those are really the lines of code that you need to run Daft in a distributed fashion. All the other lines of code are pretty much the same. We are going to show our data frame again. Again, there's no data to display right now, but once we materialize it after we do our filtering here, I'm going to breeze through this and I'll show you the output after we do a filter. And that looks like this. Give it a minute to run. Remember now that it's running across 10,000 rows instead, so it's going to take a little bit more time. And these are the rows after running across 10,000 rows. And we actually have 2,000 rows now. So 2,000 images instead of just 16 that we saw when we ran locally. And this is all, remember, this is all now running remotely on a remote ray cluster that I have running that has more CPUs. I believe in this case, it has 16 CPUs to work with. So it should be a little bit more powerful and has more memory. So now I'm going to, again, just select the name column and show it, same output. And then now we are going to download all of the data. So remember that this is now running across 2,000 rows. But because we are running on more powerful machines remotely in AWS, this is going to run way faster. And so now we have all the bytes pulled down for all 2,000 rows, all 2,000 images. And now we can now convert them into pill images with the same code. and we can show the first 5 of those poll images. Notice that the images are different now because we are working over 2,000 images instead of just 16. But yeah, these images don't really have any red in them. And so we want to run our magic red detector and then sort to find the reddest images. So let's run our magic red detector, same code, no change. Let it run for a little bit. And then we will also run these functions to sum up all of the red pixels and then sort them in descending order in order for us to capture the top reddest images in our collection of 2,000. So in this case, the magic red detector is running, and it looks like these images are not red at all. We have one right here, which is just red seats, and a red car as well. So it's working, and it's running over 2,000 rows. And now we can sort over all of these images. Ignore these warnings. NumPy and Pill don't seem to get along in certain versions. But yeah, now we have all the reddest images in our whole data set of 2,000, right? After filtering, it was 2,000. And looks like these watermelons are really red. There's a red flower. And so this is really useful, for example, if you are trying to debug your system's performance and you're like, hey, for some reason, my system isn't performing really well on red images. Let me use something like Daft to identify these red images, filter them out, maybe retrain my system, or use this data as like a test set to make sure that my system is working consistently over these images. So yeah, that was it for the demo. And to recap, let's do a little bit of recap. So Daft provides us with this familiar Dataframe interface. As we've seen, that's really useful for doing relational operations such as filtering the rows, joining 2 tables, or running computation across an entire column. It has a really expressive typing system, which makes it, which allows it to support, like Python objects from Pill, Python objects from NumPy, and it's really powerful at providing you with Python native UDFs. Some examples that we've seen were UDFs to run our magic red detector, or to run our conversion from bytes into Perl objects. And those are really easy. They look almost exactly like they look as a normal Python function. And last of all, Daft is distributed. So we saw an example also of how we ran locally on a small subset of our data. But once we were ready to graduate into the cloud, we could then run Daft on a distributed cluster of machines on Ray to run it on a much larger pool of compute resources. Yeah, that's all I had today to present. We are hiring, so if any of you are interested in databases, compilers, or distributed systems, come chat with us. We are actually in the process of building a lot of our functionality out in Rust. So if Rust is something you're interested in as well, come get in contact with us. A lot of our internal kernels are moving over into Rust. Our expression systems, all the typing is also moving to Rust. And ultimately, I think our goal is to make the most Pythonic, user-friendly data frame available. And we are already running faster than a lot of the data frames out there. And so we're really excited to make Daft kind of like the de facto solution for processing data across the primitive to complex spectrum. Yep, that's it. I'm happy to take questions. I see Hamilton has a question. What's a good attribute, complexity, number of cells, anticipated data growth for determining when it's a good idea to consider using Daft? That's a really good question. Honestly, if your data is completely tabular and it can fit within one machine, you should probably use something like pandas or polars. If you don't need any of the functionality that Daft provides, such as the ability to scale to a distributed cluster, or if you don't need any of the ability that Daft provides for images or complex data types. So if you're only dealing with dates, if you're only dealing with strings, ints, these fairly primitive data types, I would up to, I think the metric that I've heard at certain conferences is for pandas, it usually performs pretty well up to tens of gigabytes. So if you have like a 20, 30, 40 gigabyte data set, you can usually provision a big enough machine in AWS to handle it. And by big enough, the benchmark seems to be 10x the size of your data. So if you have a 40 gigabyte data set, if you're using pandas, you should try to provision a 400 gigabyte machine. And Blake is asking, how does Daft compare to Dask? So that's really interesting. Dask actually has a data frame as well. It's called the Dask data frame, and they distribute over the Dask framework, which is similar to Ray. There are some differences, but I think that's kind of a whole talk on its own. So in terms of how we compare to Dask, Dask has a very rudimentary query optimizer. So we're actually starting Daft off with a full context of, hey, like what makes a successful data frame? And we've seen that lazy data frames and query optimizers are crucial for performance. So that's something that we're focusing on really early on. And we're also building a lot of our internals in Rust, which allows us to outperform a lot of these other data frames. We have benchmarks, but they're not public just yet. But they're very promising compared to a lot of these other data frame libraries. Are there particular use cases in Daft targeted to perhaps missing capabilities in Dask? So yes, also because Dask has kind of like pandas compatibility, right? So we don't do any pandas compatibility. If you notice, our APIs are just like not pandas APIs. And that's because we want to be able to support these really powerful use cases. For example, if I come back to my example right here, in some of these UDFs, where's my UDF? Here, this UDF. If you notice, I actually had the ability to request for resources. And one really powerful part of Daft, you can actually do num GPUs equals 1 or 2, right? And this is something that most other frameworks don't allow you to do. And in this way, you can actually parallelize GPU computations and really control the execution of your data frame. Okay, Pat is asking, what are some of the other things that are coming next for Daft? That's a great question. Personally, one of the things I'm most excited about is that we are looking at introducing actual types for these complex data. So instead of seeing, so instead of seeing a Pi image type, right, this is just a pill type, we're going to be introducing ways to extend the typing system in Daft so that we can provide you with a Daft native image type. And that comes with a whole bunch of benefits because we can also start providing you with types such as a Daft bounding box type, right? So then now you can draw these boxes on your image, you can start doing crops on your image, and we can provide you with native functionality to work with your images and all of these associated funky associated types. So in biology, for example, we have genomic sequences, right? And there are these operations with genomic sequences that you may potentially want to do, and we can provide that out of the box as well with what we're calling Daft types, which is up and coming. So the issue actually with these Python image types is that like when it comes to serialization, it's really difficult to think about how do I store my data? Like, do I want to store this data as JPEG? Do I want to store it as it's raw like bytes? Having a Daft type helps us make these decisions and provide that optimal user experience. And so if you want a pill image type, you can just call my image dot to pill, and then we can give it to you as pill. Otherwise, we'll keep it as a Daft image, and we can work with Daft images really easily from within Daft itself. Yep, I think those were all the questions. If anyone has a live question, feel free to ask it. Blake is asking, to what extent does Daft expose lower level configuration of the Ray cluster? And should I have a Ray cluster comprising of machines with varying levels of memory? That's a great question. Daft actually doesn't do any configuration of your Ray cluster, right? So if you notice up here, all this configuration, this is pure Ray. It has nothing to do with Daft. All I did was connect Daft to Ray after initializing it. And so in terms of configuration, you actually even need to install Daft on your Ray cluster to get it to run. And so really everything else is kind of like Ray detail, but I can give a couple of good best practices for Ray to give you an idea. So for Ray, it's often easiest to just keep things simple and have a homogeneous cluster, meaning you can just have a single machine type, and then you just provision that across your entire Ray cluster. That being said, Ray does support heterogeneous clusters. And so you can, for example, have some machines that have GPUs and some machines that only have CPUs, or have some machines that have more memory. And in so doing, Daft can actually provision these UDFs more efficiently. For example, if I run a UDF, where's my UDF again? Right here. So if I run a UDF that needs GPUs, then Daft will ask Ray to, hey, like this UDF requires GPUs to run, and then Ray will do the scheduling to the machines that have GPUs, right? If I say like, hey, like this, this UDF is really CPU intensive, right? Give me 16 CPUs, then Ray can also do a thing where it can, provision your UDF to the machines that have more CPUs available. And so those are all just Ray details. Let's see, any more questions? Cool, I think those may have been all the questions, but if anyone has live questions, happy to answer them. Yeah, otherwise feel free to go to, getdaft.io. That's where we have all of our, oh, it's not loading, my internet maybe is a little slow, but yeah, that's where we have all of the information about Daft itself. And yeah, stick around and feel free to ask me any questions about Daft that you may have.
Oh, we've got one more from Hamilton.
One more question.
Yeah.
Can you provide an example use cases?
On that one, Jay, I was trying to get it in there quickly before you shut the meeting down. I understand for things like machine learning and for genome sequencing and for image processing, those could be some good use cases. I was just kind of looking for things that would be more mundane. More mundane meaning something that, what would be an everyday use, something that would be more general.
If you,
well, as for instance, if you were doing some processing of, I don't know the right word for it other than web scraping.
Yeah.
Or,
that's a great question. So actually one of the most mundane use cases is, let's say you have a bunch of JSON sitting around in like a file system like S3. Let's say you have like 1 million JSONs, right? And the JSONs have like weird, like formats and like structures, and you need to parse them into like a data frame format. That's a great use case for Daft as well. All you need to do is call like Daft from files, load all my JSONs in, download them, do like json.loads, and then load them into Python, do all my custom processing, and then dump it back out. That's a great use case for Daft as well, where you have all these. I would also classify them as complex data because oftentimes the schema of this data, you can't really make any assumptions, and you need a lot of custom processing for this data. So we've seen examples of processing JSONs, protobufs. If you're familiar with the format, is also another example where people have a ton of just protobuf files that they've been logging from machines and just dumping somewhere, and they want to load that into Daft, process the protobuf, explode it into a data frame, and then save it as like a CSV or a Parquet file that makes it much easier to deal with downstream.
Yeah, I have another question.
Please go ahead.
I haven't heard anybody mention it yet today, but I'm just wondering if there is sort of a use case in the area of language, like translation services or something like that.
Yeah, great question. So, you can represent text in your column as well. And also Daft works pretty well if you want to represent tensors. And so that's a pretty common use case where you might want to do something like tokenization, right? Where you have a sentence and you want to tokenize each word into a vector and then have this tensor be a column, and you want to then run a machine learning model over these columns. So that is an example use case. I believe we have a tutorial somewhere as well. It might not be in the documentation just yet, but we have a tutorial where we run the DALL-E model to run on these like text and generate images from the text, which is a pretty fun little exercise you can do. But for translation, for example, what you could do is you can have maybe an English text column, and then you can run translation models to produce other columns, Chinese, Japanese, or like I don't know, Arabic, and all these other languages, and then you can have this like nice tabular representation of what you're doing. Does that answer your question?
Yes, very well. Yeah, I was thinking of if you had a document and you wanted to translate it into, I don't know, maybe what are there 20 or 30 languages in the world?
Yeah, I mean, if you had the document, oftentimes these documents come in as like PDFs, HTML, and it's tricky in a lot of other frameworks, right?
If you wanted to translate a document into multiple languages, sort of at the same time, if you will.
Yeah, and the nice thing is because you can then just define these UDFs on your data frame, and so maybe you have 16 UDFs that each translates it into a different language. Daft is going to be able to just like distribute and parallelize this for you if you're running on Ray, and so it's super simple to do without having to really build your own framework and system around parallelization of these tasks. Yeah, and I was about to say the added benefit.
Thank you.
Yeah, I was about to say the added benefit is if your data comes in the format of like HTML or something, then yeah, you can also use Daft to pull the HTML files down, do the HTML parsing, get the text you actually want, and then run your models. And so it does all these pre-processing steps pretty nicely for you as well. Tim had a question here. How do you compare Rust to Java, C++, Python? That's a great question. We actually started by writing a lot of our kernels in C++. So Sammy is actually, he's a C++ guy, and he's been writing C++ for a while now. And we actually decided to move on to Rust because of a lot of just like the type safety that comes along with it. We also really liked a lot of its pattern matching for dealing with all these really complex nested types that we're working with in Daft. And so far it's been the performance has been great. It's been running really well for us. The only downside is the lack of, I guess, like ecosystem tooling, because it's a fairly new language and ecosystem as compared to C++. And so that's kind of what we miss from the C++ landscape. But in terms of memory safety and performance, it's been working out really well for us. The reason we didn't want to use Java is because if folks are aware of or have used the Spark ecosystem of tooling, that's all built on the JVM and Java. And the issue is that we really wanted to build a Python native library. And in order for it to work really well with Python, it's much better if you build kind of like this self-contained binary, either in C++ or Rust, and then build Python bindings, instead of building this JVM thing and then connecting it to the Python interpreter, which is what PySpark does, and it ends up being really, really difficult to work with because you have to send Python objects back and forth between the JVM and the Python interpreter, and it's then really difficult to support arbitrary Python types, any Python functions. Installation becomes a pain, and it's just too painful to manage two different ecosystems. So that's the Java story, and the Python story is that a lot of our initial implementation was in pure Python, but at the end of the day, a lot of these things are just too slow in Python. And so mostly because of the GIL, if we wanted to do any sort of multi-threading, we would have to dive down into something like C++ anyways. And so now the way that Daft works is that the user-facing API is all in Python, but when we do any kind of kernel level operations, we will hop into Rust and do it in Rust instead. So that's a big refactor that's coming actually around, I think, maybe in two more releases for Daft. We're moving a lot of our kernels into just Rust so that when we run Rust, we can fully release the GIL and make use of all the parallelism and threading on that level. Hope that answers the question, Tim. Blake has another question. Oh, DVC, yes. So you use DVC for maintaining binary data. That's awesome. I would love to talk to you about DVC actually. Does Daft have intermediate hashes of the chunks of data used when a distributed access is used? So you can think of Daft as like the in-memory processing pipeline, right? So for DVC, it versions the data on disk, right? So that's your kind of like serialized storage format. But if you want to go from one I guess like data set to another, then what you do is you load it all into Daft, do your processing, and then dump it back out. So Daft doesn't really have the concept of like intermediate serialization. You could, by writing your own UDFs. So that's something you could do. When you get to a certain stage, maybe you can write the UDFs out into your DVC storage and then continue and have the processing continue. But no, that's not something that we currently have. But I like to learn more about what you're doing and see if this is something that we should be building into our system. We are starting to think a lot more about data versioning and how we should have Daft work with tools such as DBC, Iceberg, Delta Lake. And so if this is something you have a strong opinion on, yeah, come talk to me.
Last call for questions, folks.
Thank you all. Great questions.
Thank you so much, Jay. We really enjoyed your talk. I think the number of questions you guys see tell you about that. Thank you so much for speaking with us. And if you ever want to speak for us in the future, just let us know.
Sounds good. Always happy to come back to speak.
Jay, I do have one question.
Yes.
Can you fit something related to commanding a tank squadron into your next talk?
I don't know where you dug that out from, but yes, I'm from Singapore, so I used to command a tank company in Singapore before moving to the US. I will see. Maybe I can weave it somehow into the demo of Daft. That could be interesting. I'll come back to this meetup and show the new demo if I ever have it, I guess.
Okay. We are going to have the record or the video of this talk up on our YouTube channel within about a day or so. And that's the Hsv.py YouTube channel. So we can all review it there.
Thank you. Oh, I guess I'll also drop my email in this chat if anyone wants to get in touch. Or yeah, it should be in the recording as well. It should be somewhere at the end of the recording.
Oh yes, thank you very much. I think you had it on your one of your title slides, but that was perfect. Thank you. All right, if there's no other questions, we'll go ahead and conclude this meetup. Thank you all for attending, and thank you so much, Jay, again for speaking for us. And we'll definitely be in touch.